Thank you very much for the introduction. Can you hear me? Okay, very good. So my name is Giancarlo Pellegrino. I'm a postdoc researcher at the Saarland University in Germany, and this is a joint work with Davide Balzarotti, is professor at Eurocom in France. This is the institution where I got my PhD. And in this presentation, I will show you the results of one of our recent works on compression bombs, which apparently are striking back. Now, let's start with this slide. So we use applications every day, web-based ones, and these applications rely on a number of core services. These services are like web servers, email servers, instant messaging services, and all these services are communicating with each other and with clients to support basic functionalities of modern applications. Sorry. Now, the amount of data that is exchanged between these services is increasing over the time. More data to exchange means that you need more time to transfer data, you need bandwidth to support that. It means the system may become responsive, and this ultimately leads to unhappiness of users. Now, if you want to deliver your service to users, you should fix this. You should make your system responsive. One approach is to, this is an example of how big pages are becoming. There was recently, or even, I saw this last year, but this year appeared again. The average size of a web page is about 2.3 megabytes, including images, CSS, and JavaScript files, which is the size of Doom, for who of you is old enough to remember this glorious game. Now, one way to solve this problem and to improve responsiveness of your system is to buy bandwidth. But of course, buying bandwidth means paying someone that delivered the service to you. So this, let's say, it's a solution, but nobody's happy to pay if we can do better. So the other solution is to start using data compression. Now, data compression in general is a coding technique. This coding technique allows to reduce the number of bits that we need to use to represent a string. This trick consists on removing redundancy. Sometimes they just remove, let's say, information that we can live without. Depending on the strategy, a compression algorithm could be lossless if, for example, decompressing the compressed data returns the same data. Otherwise, it's lossy if some data is lost in the process of compressing and decompressing. For example, lossy is used for compressing videos, audios. Our eyes and ears are pretty good in reconstructing the missing information, while lossless fits pretty well for documents. Imagine that you compress and decompress a document and then you're missing bytes. Nobody would be happy to have such a feature. There are several algorithms to compress data. You can refer to this book here, really mention everything about algorithms, from the principles until the implementation, libraries, tools, and so on. Amongst the popular algorithms that we use every day, we have deflate. Deflate, I think it's the only compression algorithm that is standardized in the sense that there is an RFC, 1951, that explain how this works, how this is implemented. And there are several libraries and tools implementing this algorithm. The most notable one is zlib. Zlib is implemented in mainly, literally, all operating systems that we are using, regardless if it's Windows, Mac OS, or Linux-based. Or you can use it. This algorithm deflate is used also by tools like gzip, or is used by archiving tools like zip tool. And furthermore, the deflate algorithm is also available in most of the programming languages, PHP, Python, C, C++, just name it. Now, as I said, compression is a technique that would allow to save some money if you want to exchange data, increase the responsiveness of our system. Compression is used by network protocols, and this is used to reduce the size of messages being sent. Doesn't matter if it's a stream-oriented protocol or a datagram-based protocol, you can apply it in any case. The use of compression in protocols can be mandated by specifications. This is, for example, the case for HTTP. There is the HTTP specification explains how to compress, but only the response. IMAP, there is also IMAP compression document describing how to do that. XMPP, SSH, point-to-point protocol, and many others. Compression in protocols can be also a custom feature. In this case, is not a specific. You won't find it in a document. You will find it is a feature documented in a specific software. For example, mod deflate of Apache HTTPD supports compression of HTTP requests. Now let's have a look how compression works in HTTP according to the standard. So this is a very simple HTTP conversation between a client and a server. It's pretty trivial. Imagine the browser wants to access to the Wikipedia homepage. What it's doing, the browser, after the user type www.wikipedia.org, the browser will prepare a message like this, open a TCP sockets and so on, and then start writing the sequence of bytes. The new line is not represented, but here there should be /r/n. Now, this is a get message. There's the host header, that is the domain where the Wikipedia is operating. As soon as the server receives this request, it will retrieve the default page. The default page is specified by here, by the /, and will provide it to the browser with an HTTP response. Is at 200 OK, meaning I found the document. The content length says how many bytes is contained in the document that is going to be delivered, and the type of document. In this case, is text/HTML. And following, there are 2 empty lines, and then here starts the HTML page of Wikipedia. And the size of the body, this part is called body, is exactly this one. So the browser, as soon as it reaches the last byte, it will just stop reading the response. And obviously, the browser then renders the HTML page to the user. There will be some other interaction depending if the HTML code contains other URLs, other resources. The browser will, fetching all these resources, at the end will render with nice pictures and interactive JavaScript. Now, the size is 80K, is not the size of the original page was 80K. It's not representative in terms of size. It's not the 2.3 that I showed before. But if we reduce the size of each page every time we, especially if it's a text resource, every time we download, we start having some gain in terms of bandwidth, spared bandwidth. Now, compression HTTP works as follows. First, when the client, the browser, is requesting a resource, it can declare what type of encoding supports. The encoding is how the resource is transformed before being sent on the wire. In this case, I showed only 2 cases that refer to compression. Doors are open also for other type of encoding. You can just come up with one, get a name here, and as soon as the browser and the server can understand this encoding, you can use it in your HTTP conversation. So the browser says, I understand gzip and deflate. So what the server is doing, it will pick one of these, gzip or deflate. It decides which one wants to use. And at this point, things depend from how the application is implemented. The web server can already keep a stored copy of the HTML page compressed, or can apply the compression on the fly. It fetch the pages, compresses it, or just fetch the compressed page, and send it to the client. The differences with the previous non-compressed resources that the content length is matching the size of the compressed resource, is not anymore the uncompressed one. And the content encoding specify how to decode the body. And of course, content type is still the same as an HTML page, the document being exchanged. Now, if you compare this number with the previous one, was 82K, we have a gain of 70%. So if you start summing up this, especially with documents where redundancy is quite common, for example, text documents, you can imagine HTML, the same letters, we are using an alphabet that has 27 characters plus numbers and maybe some other special symbols. So we can gain we can save some bandwidth. Now, data compression seems very good, but there are problems. There could be some problem. Now, first of all, if it's not properly implemented, I will show you later in this presentation what does it mean improperly implementing data compression. An application can be made vulnerable to denial of service. Denial of service is one of the worst thing that we have seen in the last decades. Now, the risk of using data compression are three. First of all, compressing and decompressing is an intensive task. Intensive means that it's an algorithm that is not, for example, it's consuming CPU. It can take memory because while decompressing or compressing, we will need to store temporary data somewhere. And if this is abused, all these resources can be exhausted. The second risk is that data compression implies data amplification. Data amplification means that you process 1 byte, and as a result, you have n bytes. Now, this change of proportion between input and output is called data amplification, and internal components and services may not be designed to handle a high volume of data. Consider, for example, here, I'm making an example of zlib. The theoretical limit compression rate, meaning the ratio between the size of a compressed data and the size of an uncompressed data, is 1 to 1024. It means that 1 byte of a compressed data can be decompressed in 1K. This is in the worst case. Of course, the average use is way below than that. But as bad people, we would like to start using this to do harm. The third risk is that when we use compression in protocols, we are introducing an unbalanced scenario in the sense that one party can pre-compute compressed messages and send them to the other party. Could be a client, could be a server. The other party has to decompress all the time, has to do this, has to take the effort of running the decompression algorithm all the time. Now, in the past, and by past I mean 20 years ago, we have seen something going in this direction. So the most famous attack exploiting data compression is the zip bomb. It's 1996. In terms of computer security, we are talking about prehistory here. So the zip bomb, a zip bomb is a file. The original one was 42K. And if you try to decompress it, fully decompress it, you end up expanding it in 4.5 petabytes of data. Now, this is how this file what this file contains. So we have the root of this file is the name of the file is 42.zip, contains 16 files that are also zipped. This continues for 5 layers, and the last one contains 16 files, and each of this file, you have to imagine this tree expanded, this file contains 4.5 gigabytes of the letter A. And here is when you start seeing the 1-2,000 gain in using compression. Now, if you compress this file, you compress all of them, all this tree is only 42K. Now, this file was used to attack antiviruses. The trick was you just attach it to an email and you send it to the person you want to have fun with, and then you just wait. What happens is that the antivirus will try to open the first layer, sees that there are other zip files, is looking for malicious content, so keep on opening until, of course, there's no more memory available and the application crash. We have seen also similar problems later on, is the billion laughs attack, or the XML bomb. In this case, there's no data compression used, but the behavior of this vulnerability and the way this was exploited is very similar to zip bombs. So this is how it works. So this was a vulnerability that started in this library, libxml2. Other library were found vulnerable. And what happened is, starting from this XML file is just 810 bytes. Processing this file can lead to an XML file that can be 3 gigabytes big. So basically it starts from this part here, lol9, that is an entity defined here. This lol9 is expanded in this, I don't remember how many are them, like 10 possibly, in 10 lol8. Each of this lol8 is expanded in 10 lol7, and so on and so on and so on, boom. No more memory. So this was the attack, is what is called billion laughs, because there are billion of lols. Now, we're talking about problems that started 20 years ago. At this point, we would say, okay, we learned the lesson. We know how to handle data amplification. We know how to write robust software. Now, do you think that we know better now? What is your guess? I mean, I wouldn't be here if the answer is. Okay, so of course, the situation is very complicated. The first thing I did was going through protocol specifications. I mean, protocol specifications are saying how to use compression. Let's see what they exactly say when it comes to compression and security. So my general judgment, I'll give you already here my conclusion, is that there is an awareness of the security risks. Guidelines on how to implement properly or to handle data compression is completely missing or even misleading. I'll show you examples of these points. So going into the details, for protocol specifications, one thing that I notice quite often is that if you start looking for security concerns when it comes for compression, often you see, have a look at the SSL TLS specifications. They do security, they know how to handle compression. So any security concerns, you can find it there. But SSL TLS has different concerns than other protocols like HTTP or XMPP. For example, SSL is concerned about, for example, data leakage. We have seen some tiny problem when using compression and encryption algorithms where sensitive data can be leaked. So this is one concern they have. This doesn't apply, for example, to XMPP. I mean, could apply, but not for how to handle data compression in the sense data amplification and so on. So the point of how to apply data compression in higher level protocols is still unexplained. Second, we said, okay, this is what protocols are saying. Let's go a little bit up on the layer of type of documents that developer has to go through to build something secure. Let's have a look at secure design patterns. There are design patterns that that address denial of service concerns. These are 3 I found in one paper. I forgot to mention what is the paper. I think I can circulate the reference to security design patterns. So there are 3: denial of service safety, compartmentalization, small processes. But they are too abstract. They're just saying how you should design your software in order to limit the damage of a denial of service. Like small functions, isolate the components that could be at risk, and so on. None of them applies to the concrete problem of handling data compression. So we have no information on how to build a secure architecture that handles compressed messages. Second, okay, now let's have a look at code. Is there any book that tells us how to implement securely data compression? There was only one rule that we found. There is an anti-zip bomb coding rule. We said, perfect, that's the one. We are done with our research. But this code pattern was vulnerable. I'll show you also later in this presentation the specific vulnerability they were introduced. And if any of you implemented an anti-zip bomb procedure according to that rule, please consider to have a look at your code again. Now, that's the situation. So apparently, seems like that we haven't learned that much. But now the point is, do we have vulnerable software out there? Are we using software that is vulnerable to resource exhaustion vulnerabilities that can be used for denial of service? And that's what we are going to have a look at now. What is the impact on implementations? I will start with, I would say, a known attack for me because I spent quite some time in researching on this, but I have the feeling that it's mostly unknown. This is the last slide on how to apply compression on an HTTP response. In this case, it's possible to mount an attack using the HTTP response compression. This is a work that was presented in a blog post by Jeff Jones. Nothing I have done. I'm just presenting this one here for completeness to give a feeling on what is the current situation. So the attacker here is a server that prepare a document just once, store it somewhere, that contains 4 gigabytes of white spaces or the letter A, B. You need to have a uniform string with the same character. These are the strings that can allow you to reach compression rates of 1 to 1,000. So here I'm taking the example of 4 gigabytes, but Geoff used even terabytes of data. Now, 4 gigabytes once compressed, 4 gigabytes of space, when compressed, can be reduced to 4 megabytes. Still quite a big resource, but considering the average speed of our internet connection, that shouldn't be a problem. So the result of this attack is that the browser will try to decompress. I have to be honest, one single request of this type is not that problematic. I tried this myself. Okay, I shouldn't mention which browser was crashing because I don't remember exactly. But if you do this in parallel, you can imagine you can write a piece of JavaScript code that is using a synchronous request or using multiple iframes to retrieve the same resource. And you can amplify the result. So that's what is happening. This is the attack framework. Now, let me add one information before jumping on the next slide. The content encoding lists the encodings that the browser needs to follow to get the original resource. What happens if we add another gzip next to it? Will the browser accept that? Well, Jeff showed that, yeah, this could work. You obtain a file that is even 1,000 times smaller and obviously even more damage. Now, the way you can use this is not to reduce even more 4 gigabytes of data, but this opened the door to even terabytes of data, even more than that. So you can really explode. Now, this is taken from his blog. Have a look at it. He has also a tool. His blog post is called Vulnerabilities That Just Won't Die. He was working on this, or he came up with this blog post when I was working on exactly the symmetrical sort of work. And most of the browsers are still vulnerable. It's let's say the information to get is that this is a problem. Browsers kind of overlooked on this, but of course it's a little bit understandable because there could be some scenario where this type of attack makes sense, but it's not, let's say, so problematic. The real scenario that we were interested at is, but we want to attack servers. The attacker is not the server, but the attacker is the client. What type of damage can we do there? So the question is, the initial question of this second part of the presentation is, what is the impact on implementations? So we set up as good scientists, we did an experiment. This was our infrastructure. We just set up a server. We installed an internal monitor. We use PidStat. It's a tool available on Linux systems. And PidStat is pulling from the proc file system to see resource consumption like CPU usage, memory usage, file I/O, disk I/O, and so on. And this is the server that we targeted. We targeted 3 protocols, and then we looked for the most prominent implementation: HTTP, XMPP. XMPP used to be called Jabber. I discovered that Jabber is not a word used anymore. It's XMPP now. And IMAP servers. And then we used 2 external machines, one that behaved as a user to see how, to measure the delay or the responsiveness of the system, and the other one is the attacker. We use multiple machines, 3 exactly, that continuously are sending compression bombs. Now, how these compression bombs look like? So as I said, HTTP response compression is part of the standard. What is not in the standard is the compression of the request. Now, the compression of the request is an implementation-specific feature. So maybe there are out there web servers that don't even support that. In this case, we looked for web servers that support it, like Apache. It does support it. There are other web servers, if we can call them like that, like Tomcat. Doesn't support it natively, but you can add filters to include the feature of decompressing post data. In this case, if you want to build a message, an HTTP bomb, if you allow me this term, you have to include this header. You have to specify that the message that you're going to send is compressed. Now, this is not part of the standard for a simple reason. Usually in protocols, you need a negotiation phase. You need that client and server, the 2 communicating party, agrees on algorithm being used. That's why for response, it's more simple, because the client can say what he supports, and then the server picks which algorithm to use. In this case, we have a client that just sent a request that encoded with a certain algorithm, and the server may not support it. So this is how it looked like, and the body, in this case, is a SOAP message. Now, I'm showing a SOAP message because we wanted to recreate a realistic scenario. We wanted to find a reason or a realistic message that can be, let's say, turned into a bomb, which makes sense in a web application. So we used SOAP. SOAP is a protocol that allows you to call function remotely using XML to tell the server which function you want to execute, what are the parameters, and is XML based. That's the structure. You have an envelope, you have a body. The body is according to the SOAP specifications. I'm not going to discuss here about SOAP specification. The important part is that we wanted to create a valid SOAP message, which is an XML file, which is 4 gigabytes big, and the parser would accept it. So the idea is, okay, let's put white spaces between two valid syntactical elements. So I said, okay, let's put it between the envelope and before the body. That's a syntactically valid XML file, and let's compress it. So 4 gigabytes were roughly 4 megabytes. We did a similar thing for JSON objects. There is, actually I don't remember if it's standardized, there is a way to have remote function calls using JSON. It's a similar principle, but instead of using this puffy XML file, you can use lean JSON objects. And the idea is the same. Let's put 4 gigabytes of data inside the two syntactical elements. Similar thing for XMPP is XML message. We have 4 gigabytes of space between syntactical elements. This is still valid XMPP message. And for IMAP, this was even easier. We created an email with 4 gigabytes of empty message. Now, these are the services that we tested. We had a look at OpenFire, ProsoDT Gaze, eJabber, Jabber2, Apache HTTPD plus Modflate. We also tried something else on top with PHP, also Modiflate, other remote procedure calls, GSOAP, ModDAV, and Tomcat with 2 filters to support decompression of requests, Apache CXF, JSON, various JSON RPCs, and Axis, and also JSON RPC4j, Axis2, GSOAP standalone, and 2 IMAP servers. So we tested all of them, and the result is compression bombs everywhere. So these are all CVs that were open, and in other cases, we prefer to approach developers independently. Now, after we realized that this was a problem, we said, okay, what is wrong with software? Now, it's easy to blame developers, but at this point, when I discovered this, I suspect that the problem is not of developers, it's our problem. Our problem as security community. We failed in delivering this problem to developers. We didn't build knowledge on it. And how this reflected specifically in applications. So we had a look at all the problems in all softwares. We talked to developers to understand what they did wrong and why they did wrong. And we come up with 3 classes of problems or pitfalls. There are pitfalls at the implementation level, at the specification and configuration level. And more specifically, we found 5 issues in the code, 3 in specification, and 3 in the configuration. I picked 5 of them, and I will present them today. For the rest, I would like you to have a look at our paper. Was presented at Usenix last year. You can download it, read it for free. Okay, let's start with pitfalls implementation level. So this is an abstract representation of how incoming messages are processed. There is a pipeline, a message is here, enters, there is an authentication phase, meaning is the user sending this message a valid user? Then after this phase, there is a validation where the question is on the message level, is this a valid message? Then there is the decompression phase, and then there's the parser saying, okay, let's give a meaning to this file, or let's parse it syntactically. The meaning is given by the application, which is out of the picture. For a web server, you can imagine it's PHP or the PHP code running on it. Then there is a component, the logger. As soon as something goes wrong, there is a message for the logger. Please keep track of this message. Something bad happened. So the first problem was compression before authentication. Now, if you look at the specification, there is inconsistent best practice. In SSL, TLS is mandatory. It's mandatory authentication in the form of message authentication code, or even for the party that are authenticated. Is recommended in XMPP, is undefined for IMAP and HTTP. There is even the case of HTTPS that diverge, but diverge in a secure way. That is, compression is postponed until the user is authenticated. Now, developers, if they look at this variety of behavior, they can get confused, and they can just do whatever they think is best. And sometimes happen situations like Prosody, for example, that accepted compressed messages before the authentication. And the vulnerability was deeper in the application, but this allowed to mount a denial of service by an authenticated user. You didn't need to have a Jabber account. The second one is improper input validation during the compression. Now, input validation usually means let's see if the message fulfills certain criteria. In our cases, we don't want to decompress a lot of data, so we want to put a limit on our resources. So there are three ways of doing this. First, we receive a compressed message, and we say, is this message of the right size? So Apache mod deflate, it was taking this decision according to the size of the compressed message. But as we have seen, 1 megabyte can be decompressed in 1 gigabyte. So this, we marked it as, that's a problem. We notified this to the Apache developers. They agreed that this was an issue, and they come up with a new solution. There is a new way to configure a mod deflate to compress or decompress. And this is based on the compression ratio and number of violations. So basically, you as a system administrator, now you define a compression ratio. For example, it could be 1.2, meaning that each byte cannot be decompressed to 1.2 bytes, for example. And you can also specify how many violations are going to happen before rejecting the message. Now, this could work, but there is one problem. We're just shifting the problem from one domain to another one. Here, we have to choose about a ratio. Now, what is the proper ratio for a web application? It depends from so many things, like how the application is used. What is the type of message that we will receive? The risk here is that it's not developers, but who is going to deploy the application may underestimate this information, may be even not aware of what is the exact ratio to use. So this is a bit risky, but this is how Apache actually is implementing the validation of incoming messages. The correct way to implement this is to decompress a message in chunks, and every time counting how much data has been decompressed upon a certain threshold. This threshold is exactly the size of the data that we are willing to process. That's surprising somehow. Mod deflate, the one that was behaving in this way, actually behaves well with moddov. Now, I don't know if it was moddov that is enforcing this type of behavior. The point is that the configuration parameter used by moddov is limit XML request body, while the one used by default mod deflate is limit request body. Another problem is communication between units. The behavior that you would like to have is, as soon as there is a fault, doesn't matter where, the file is invalid, it's too big, we would like the whole pipeline to stop. We don't want to go on anymore. Let's send an error message to the user, and that's it. Now, mod PHP and mod GSOAP limit the amount of data that they can take in input. And as soon as this is done, they don't process any more input. The point is, if there is mod deflate before mod PHP, mod deflate is not going to stop decompressing, even if the limit of mod PHP or mod GSOAP has been reached. So there are no means to halt mod deflate of decompressing. This results in CPU exhaustion. And this problem was addressed in the previous CVE by the Apache developers. Logging. This is another interesting feature we have found. So as soon as something goes wrong, we want to log the message. In this case, Apache CXF, if you send a message, compressed message to Apache CXF, you send, and in the message there is a mismatch. The content type doesn't match the real content. For example, you say this is an XML file, but you send an HTML or a JSON or something else. Now, if this message is compressed, what CXF used to do was to store it on the disk, start decompressing all of it, just to take only the first 100K. Now, we find out that with one single request, we managed to write on the disk 8 gigabytes of data, that is 4 gigabytes per file. And these files were not deleted. So if you keep on sending, you can exhaust the whole disk. This problem has been solved, but was triggered only by sending a mismatch request with a mismatching content type with the actual content. Now, these were my favorite four for the implementation level. At specification level, this is the only one I'm going to show you. So this is the book we used. Again, I'm not blaming developers here or whoever tried to build some knowledge. I think the fault is more on our side as security researcher, just to clarify, even if there is the cover of the book here, it's just for information now. So this Java coding guidelines contains coding rules that tells you how you should implement securely certain features. One of this is how to protect yourself from zip bombs. This piece of code here is taken from the anti-zip bomb code that says this variable here is a zip file object instance that you can create passing the path of the zip file you want to decompress. And it says if the size is too big, where too big is a constant, is the validation that we want to do, then reject the message, throw an exception. Now, the point is that the get size is returning a value that is contained in the zip header. And the header is not integrity protected. You can create a zip file with the uncompressed size, which is 0. Any zip tool will accept it and decompress it. So you can basically bypass. You can forge a zip file. You can bypass the protection that was suggested. We notified this, and they implemented a safer solution based on decompressing the message in bytes. Now, in this slide is how we mapped implementation and the pitfalls that we found. I would say it's mainly a systematic problem that we have found. You can find this table and a nice explanation with all the details in our paper. Unfortunately, I won't have time, I think, to go through it. OK, let's conclude and leave some room to you for questions. OK, so compression bombs are back. Actually, we don't know yet to what extent this is a problem. Maybe this research is over, like we're done. Maybe not. Maybe there are devices, small devices especially, that they have constraints in terms of resources. We may want to have a look at it. And the unbelievable things for me was that after 20 years, we haven't learned how to deal with compression data. So in our research, we discovered 10 vulnerabilities, and we tried to build some knowledge in order to help developers and software engineering to build more secure services. Thank you very much. Questions? If I try to do harm to any servers. No, I did not. All our experiments were done in a controlled environment, that is in our lab. So the only harm we did was to our own servers. We didn't try out there just for ethical reasons, as we were more interested in studying the problem rather than messing up with the production servers of other organizations. Thank you very much.